Okay, so this really important summary, let's repeat it. To use NP lemma with two steps to find rejection region, then the test is most powerful at level alpha. At level alpha for single-sided testing. So this conclusion is very important in statistical testing. It is the first important conclusion in theoretical statistics in the knowledge of hypothesis testing. Okay, so for single-sided testing, most powerful level alpha test exists, guaranteed by NP lemma. You may wonder, is there any most powerful level alpha test for double-sided testing? Next natural question, is there most powerful level alpha test for double-sided testing? Let me tell you the answer. Fact, no most powerful level alpha test exists for double-sided testing. So what should we do? So NP lemma cannot handle the case for double-sided testing. NP lemma can only be used in single-sided testing. Okay. So what do we do since we cannot find most powerful level alpha test for double-sided testing? What we do for double-sided hypothesis testing? There are many test procedures can be considered as good ones. Why many can be considered as good ones? Because there's no most powerful. The key, there's no most powerful level alpha test. So some test works pretty well in some cases. So since the most powerful level alpha test can be, in some sense, you can take this as best. Write it best one. But since theory tells us there is no best exists for double-sided testing, then we can propose many. So for double-sided type of testing, there are many test procedures. Many test procedures can be considered as good ones. So since there are so many candidates, test statistic can be considered. We introduce one popular way to find test statistic for double-sided testing. Okay, so this which is one popular way to find test statistic for double-sided testing. Okay, so this way is called likelihood ratio test statistic. So this is second topic of today's lecture, likelihood ratio test statistic. So how likelihood ratio test statistic is defined? So let's first consider a specific example. So this double-sided testing, H0, mu equals mu0, and H1, mu not equal to mu0. So in likelihood ratio test statistic, we first rewrite our hypothesis testing in this way. So we rewrite mu equals the parameter space for null space. So in this specific case, null space is just one value, which is mu0. And so this parameter space is mu equal mu0. So it's a single point on the real line, and this is H null. H1 is mu equal the parameter space H capital theta. We write in this way, and this is mu is in R. Here also mu is in R. Mu not equal to mu0. So this is the whole real line except one point. So this two way of writing hypothesis is equivalent. But to perform likelihood ratio test statistic, you have to first write your original hypothesis in this way. They are equivalent. So for likelihood ratio test statistic, the first step to apply likelihood. So we haven't talked about what likelihood ratio test statistic is defined, but we first state the first step of this. First step to apply likelihood ratio test statistic is to rewrite our hypothesis in the perspective of parameter space. And in this case, we denote the capital theta 0 as the perimeter space for null hypothesis, and capital theta 1 as perimeter space in the alternative hypothesis. So we should write H null as theta from capital theta 0 and theta capital theta 1, and the whole perimeter space capital theta is equals theta 0 union theta 1. So this is perimeter space. Perimeter spaces corresponding to null hypothesis and alternative hypothesis, and this whole space, whole perimeter space. Okay. So then we can introduce what is definition. Definition of likelihood ratio test statistic. So likelihood ratio test statistic is denoted as capital lambda. Capital lambda equals, it is a ratio. So for numerator, it is the supremum of theta from the perimeter space for null hypothesis and this is the likelihood function evaluated at theta. This is the numerator. For the denominator is the supremum of theta from, this is not from the alternative perimeter space, it's from the whole perimeter space, capital theta, not capital theta 1. Keep in mind, capital theta, likelihood function evaluated at theta. So the likelihood ratio test statistic is defined as the ratio of this numerator is actually restricted maximum. Restricted at maximum. And for this, there is a global at maximum. Global maximum. Okay, global maximum. So why this is helpful? Because we can use this likelihood ratio test statistic to find decision rule. Decision rule for likelihood ratio test statistic has a rejection region. Has a rejection region as a set capital lambda less than some constant k. And how to determine k? Let's review how to determine k in our Neyman-Pearson lemma 2 steps. The second step is to set alpha equal the probability. What is the probability? The probability of this rejection region, given h9 is true, set to alpha. To first step, we also write this. Second step, set alpha, the probability of this rejection region, given h null is true. We set this probability alpha. This finishes the way for likelihood ratio test statistic in testing double-sided hypothesis testing. Okay, so let's see any specific example how to find. Let's see an example. Example is random sample capital X1 orbit capital Xn ID normal is mu sigma square, but in this time sigma square unknown. Sigma square unknown. So let's first write the likelihood ratio test statistic. So how to write? So here the first step is to write in this way. Second step is to find this. So okay, let's first see first step. First step, rejection region should we write this? Okay, as we mentioned again and many times, this is notation to record any constant. So this actually is an abuse of notation, but this helps us. Our derivation is more convenient. So first, how to calculate capital lambda in this case? Okay, sorry, we don't write the specific testing problem. So test problem is a double-sided testing, mu equals mu 0, h1 mu not equal mu 0. This is our interested testing problem. So okay, actually the first step is not this. First step is to rewrite the original hypothesis testing in a perspective of parameter space. Okay, let's do it. First step, write h null and h1 in the perspective of parameter space. So let's do this. So first step is null. So mu here, theta is mu. So the original part in mu is from. So here actually we have two parameters for theta. Because sigma square is unknown, we have to take it into consideration also because it is unknown. So theta equals mu sigma square it from the null capital theta 0. And what capital theta 0 is? So capital theta 0 is mu equals mu 0 sigma square greater than 0. And h1 theta equals mu sigma square in the alternative parameter space. So what is the capital theta 1 is? Capital theta 1 is mu is in real line, mu not equal mu 0, sigma square also greater than 0. This is the This is the rewriting of original hypothesis in the perspective of perimeter space. Okay, then let's write capital lambda. So the second step is we write the rejection region. This is rejection region form. We write the rejection region in this form, so we have to find what capital lambda is. Capital lambda by definition is the sup theta from capital theta 0, L evaluated at theta, and the denominator is the supremum of theta from theta 1, capital L, theta, not the one, the whole, not the one, the whole perimeter space. Here, theta, capital theta is capital theta 0, union capital theta 1. Okay. So let's first find what is the numerator is. Numerator for numerator. Is sup theta from theta 0 L theta. So in our case, theta has two parts. One is mu, one is sigma squared. And we need to do what? We first need to write theta given x. X is one realization of random sample small x1 to small xn as the product I from 1 to n. F is standard normal xi given theta, and we have done this many times. So theta here has two components, mu sigma squared. Here is normal mu sigma squared, theta mu sigma squared, and you know how to write a PDF of normal distribution. We have done this many times. So you know how to find the sup theta from theta 0. Let's write it explicitly. What is theta in theta 0? So that means mu equals mu 0, sigma squared greater than 0. We need to find the maximum over this perimeter space of the likelihood function L of theta. And let me tell the result. You can do it by yourself after class. The result is the likelihood evaluated as mu equals mu 0, because there's only one choice for mu 0. There's no space for us to make it bigger because mu is considered as fixed value. And for sigma squared, it should be equal as 1 over n I from 1 to n xi minus mu 0 squared. So this way of writing is a little too long, so let's make it more concise. We don't write this. Okay, so let's rewrite it. So here mu 0, and for sigma is 1 over n I from 1 to n yi minus mu 0 squared, because L theta itself actually has two parameters, mu sigma squared, because sigma squared is unknown. So the supremum on this perimeter space, the result is this. You may wonder how to get this result. How to get this result is actually, since mu equals mu 0, 1 theta in the null perimeter space, and how to find sigma to maximize the likelihood function, it is d set d derivative mu 0 sigma square d sigma square to 0, you will find sigma square equals 1 over n, I from 1 to n, xi minus mu 0 squared, not y, sorry, xi here. This is the numerator part. For denominator, we'll do things similar. For denominator, it is supremum to theta over the whole perimeter space, L theta. So for denominator, let's see. For theta again, it is mu sigma square. For the whole perimeter space is just mu in R, sigma square greater than 0, because this is the state 0 union theta 1. And let's see, so for theta 0, it is this form, theta 0. And for theta 1, it is in this form. And then union these two sets, you get theta as this. And theta, we need to maximize L theta over the whole perimeter space. What should we do? Actually, we should do the partial of mu sigma square divided by mu. Set this to 0. Also, set this also to 0. Then solve. You will find what? Mu should be small x bar, and sigma square should be 1 over n, I from 1 to n, small xi minus x bar squared. So which means what? Which means the supremum of this likelihood function on the whole perimeter space is what? Is likelihood function evaluated as what? At x bar, and this is for mu. And 1 over n, I from 1 to n, xi minus x bar squared. This part is for sigma squared. Okay. Now we have got the result for numerator and denominator. Let's rewrite it as follows. So numerator sup theta from the now of this perimeter space, L theta is L mu 0 1 over n, I from 1 to n, xi minus mu 0 squared. And for soup, theta from the whole space being the denominator, L theta is L, this small x bar, 1 over n, I from 1 to n, xi minus x bar squared. And then we got this likelihood ratio test capital lambda, which is defined as supremo theta from theta capital theta 0, L theta divided by sup theta from the whole parameter space, L theta, and then we plug in the result for the numerator and denominator, which is L mu 0 1 over n, I from 1 to n, xi minus mu 0 squared divided by L x bar 1 over n, I from 1 to n, xi minus x bar squared. And after plugging this, our first step is lambda less than k, and we plug in, and we keep in mind that k is just a notation to record some arbitrary constant. So this we just get what? L mu 0 1 over n summation I from 1 to n xi minus mu 0 squared divided by L. This is x bar 1 over n, I from 1 to n, xi minus x bar squared less than k. The set equation. And then that what? You can plug in the likelihood function, because for normal we know how to write likelihood function with respect to mu and sigma square. We know this, and you just need to replace mu with mu 0 into the representation of this function. And here, and for sigma square, you just plug in this result here. Also, for denominator, you here put it here, and for this part, you put here. So this is likelihood function for normal. It is a product of standard normal PDF. And you get what? You get and by doing some observations, that let's go back to the derivation of that one we have done at the beginning of this course, at the beginning of this lecture. Let's see. It's like this derivation. We first write our likelihood ratio in this way, and we observe that exponential is monotone, and this scale operation is monotone. We can eliminate, we can write it in this way. We got something like this, and we further simplify, we can get this and this. And for this scenario, the situation is similar. We have got this part. We got the ratio of two likelihood less than k, and we plug it in. We got exponential something with some factor less than k, and you can do some simplification, and you can get what? You can get I from 1 to n xi minus mu 0 squared divided by I from 1 to n xi minus x bar squared greater than k. Recall, let's do a comparison. It's like what we had done for, let's compare it again. It's like what we have done for the first set equation. You see, we have exponential here, but we can eliminate it because we have set equation, and k is keeping changing, but we always write k, and we got this summation, subtract summation less than k, and then finally we get something greater than k, and they are equal in the sense of set. And we can do similar trick here, but we don't go to detail because this is too long for our course aim. So we just give you the result. It can be simplified into this way. And then what? And then we can further simplified as x bar minus mu I squared divided by small s divided by n greater than k. So small s is the sample population, sample variance. And then we got what? We can further simplify to make it absolute value, x bar minus mu I. Can take square root mu I. Then it changes to absolute value, small s square root of sample variance divided by square root of n greater than k. K is just notation to record some arbitrary constant. We don't need to specify it at this time. So you find what? So we make an observation that this is what? This is actually capital T is T distribution, a T random variable following T distribution with degree of freedom n minus 1. So here we have got our destination. That is the first step. We can calculate capital lambda sup theta from capital theta 0 L theta divided by sup theta from capital theta L theta, and the first step is to rewrite rejection region capital lambda less than k, and we have shown that it is equal to another set. In the set of set is the absolute value of T distribution greater than k. And this T is what? T is capital X bar minus mu 0 divided by S divided by square root of n. And the next step for likelihood ratio test statistic is to set alpha probability of capital T greater than some constant given h null. So h null is just mu equal mu 0. So we have T, we have mu 0 in it. So here, then we find what? We find C should be T n minus 1 all 4 over 2. So our rejection region, so conclusion. Testing H null mu equal mu 0, H1 mu not equal mu 0. Apply the principle of likelihood ratio test statistics gives us rejection region as absolute value of capital X bar minus mu 0 divided by S divided by square root of n greater than t n minus 1 all 4 over 2. So you can see that using the principle of likelihood ratio test statistic give us our similar decision rule as we have introduced for the double-sided testing. We also have this for normal model and sigma square is unknown. We have this result, and by applying the principle of likelihood ratio test statistic, we also get this same result. So this finished our today's lecture about introducing Neyman-Pearson lemma and the likelihood ratio test statistic. So in summary, that why we introduced Neyman-Pearson lemma, because Neyman-Pearson lemma is so important in statistical theory. So theoretically speaking, Neyman-Pearson lemma told us a very important result, which is for single-sided testing, Neyman-Pearson lemma guarantees that the test statistic derived from Neyman-Pearson lemma 2 steps, it is the best. So in what sense it is best? It is the most powerful level alpha test for single-sided testing. And for double-sided testing, we have the conclusion that there is no most powerful level alpha test exists. So we introduce one way to propose test statistic, which is likelihood ratio test statistic. And we give you an example in normal model when sigma square is unknown. And we have also shown that this gives our very familiar result we have when we introduce double-sided testing for mean. That is, likelihood ratio test statistic principle give us the same test statistic. Okay, this finished today's lecture. See you next time.